Hello, it's November 28th. Another week done on Clarence Kennedy's 9 times per week program. Actually, this week feels a little bit better than last week, especially on the hard day. Thursday is officially the hard day because I have to do 3 sets of 3 cleans and a jerk. Overall, my snatch is stronger than my clean, so the snatch part is okay. I think I went all the way to 155. Which is 1 snatch plus 2 hand snatch. So it's like 3 reps at 155. This is unthinkable. Just a few months ago, it's unthinkable. But the clean and jerk is even more. I have to do 3 cleans. And remember, the ladder starts at 175. Yeah, it's, wait, hold on. No, it starts 180. It's 180, 195. Okay, that doesn't make any sense. Now it's 175, 185, and okay. Let me check. I forgot what's the weight, but it was some preposterous weight at the end. All right, here we go. Snatch, 135, 145, 155. All right. Clean jerk, 175, 190, and 200. 200 for 3 cleans. That was something. That was something else for sure. But I survived. And next week is 205. It's even more preposterous. I don't even know. But we'll get there. We'll get there when we get there. Alright, so today is an easy problem. Maybe we should start looking into this one. Or maybe not. Yeah, I don't feel like it. Let's just do this. Minimum operations to make array sum divisible. How many divisible by k problems are there? It just kept producing the entire week. It's all divisible by k. Entire week. You're given integer array nums and an integer k. You can perform the following operation any number of times. Select an index I and replace nums I with nums I minus 1. Return the minimum number of operations required to make the sum of the array divisible by k. So basically we are saying that we want the sum of everything to be divisible by k, and we can choose any number and to decrement it by 1. We're basically just saying the whole sum you can decrement by 1, and then you want to know how many decrements you need for it to be divisible by k. So all you need to do is get the sum, get, and then return the modulo. That's it. Alright, this is no wonder the passing rate for this problem is over 90%. I completely understand how that happens. So getting closer to finish the 2000 day. I'm starting thinking what to do afterwards. There are other things that I want to do. I'm gonna pick up a new hobby now. So maybe I'll do the new hobby. I have not decided yet what to do. I think this shall suffice. Yeah, this shall suffice. We have 25 days left before hitting 2000. Okay, so I have absolutely no I don't want to do these hard problems. I want to have fun. I do want to do another one. Let's do another one, but not a hard one. They don't have like a random. Can I pick a random problem? Filter, sorted custom. I cannot pick a random problem. Let's go for the last problem. Can I difficulty tag? Oh, I know. I'll go to the contest. Where's the contest? I'll go to the contest, pick the most recent contest, and pick, because for fun we pick the second one, because usually the second one is a medium problem, and hopefully I can do it. Yes. Okay, yeah, let's do this one just for fun. Find maximum balanced exclusive or subarray length. Given integer array nums, return the length of the longest subarray. The length of the longest subarray that has a bitwise exclusive OR of 0 and contains an equal number of even and odd numbers. If no such subarray exists, return 0. We want to return the length of the longest subarray that has a bitwise exclusive OR. So if the bitwise exclusive OR is 0, that means we have the same, we have pairs, right? We have every single number in it has a pair. So that's a requirement. And another requirement is we need to have equal number of even and odd numbers in it. I guess that's not exactly the case. You don't have to have them the same. Okay, I was wrong. I thought you have to be the same. No, you don't have to be the same. You do not have to be the same. Why? Let's see. 1, 1, 1, 1, 0, and 0. So exclusive OR. Ah, I see. Okay, so then what we need is to have, equal number of even and odd is a given. It has to be, right? It has to be, because if you don't have equal number, they won't have exclusive OR to 1. So this side is done, right? This side is done. We always have to pick equal number of even and odd. And what we need to find is on the other positions, they have to be the same. And we need to have the length. So at each position, so what we can try is get a sliding window. We can do a sliding window of count, because at these positions, to be exclusive or to 0, what you need is just have even count of 1, right? That's all you need, even count of 1. Yes, even count of 1 on all the other positions, and same count of 1 and the same count of 0 on the last position. So if I have a sliding window, okay, and I start counting, we count the largest that has the equal number, and then we check on the other positions, because the 10 to the 5th, 10 to the 9th, so we just need a 32, right? 32 positions, and we have a sum, right? We have a sum, prefix sum. That's fine. And we check anytime that this hits even count, what does it look like? Do every single one of them is even? If they're even, then we find, that's a good one, right? If it's not, then it's a bad one. And then what? And then you'd expand. How do you find? Okay, I want another example. I want another example. Let's do another example to get a sense of this question. So 3, 2, 8. 8 is this. 5 is this. 4. 14. 14. 8 plus 6. I think that's 14. 9. 8 plus 2, so that's 9. And 15. Okay. So we count 1, 2, 3. We have 3, so yeah, that's not gonna work. So we have 3, but if we include all of them, that's not gonna work. So I say I include.
Ask for toilet paper today?
Yes. We're gonna go to Walmart tomorrow. I go to Walmart tomorrow.
Oh, my mom said she ordered.
Hey, delivery? Okay.
Or you need something else from Walmart?
So I have ones. Huh. How long are we talking about? 10 to the 5th, right? Can we do binary search on this? Yes, we can do binary search on this. So the total length, right? The length has to be even. So we just pick the middle, which is even, and then we go sliding window, go through them, and then check every single one if it's, you know, if it's the count is correct, and if it's good, then we get bigger. If it's not good, we get smaller. Yes. Okay. Let's go binary search on this one. And we'll do a prefix sum for every single position. Now, technically, we don't have to, because we hold a prefix. Nah, let's just do it. Let's do it. I think prefix sum is much easier to deal with. And the answer is 8. I think it's 1. How his answer is 8? Did I got this wrong? 2, 3. Oh my goodness, I got this wrong. This is not 9. Dude, this is not 9. It's 1. It's a 0, 1. So you got all 4. Has 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Yeah. Okay, let's call this up. I haven't done this for a while. I need to find the previous example. Oh, here we go. Ugh, that's a pi. There we go. 3755. Okay, 3755. 3755. All right, let's do this. This is a pretty medium problem. So we will create a prefix count, right, of set bits at each position. Then we do binary search for the length, and at each trial we use sliding window to find the number to check right, to check if there exists a window, right, such that each position has even count of set bits. If that is the case, we increment the length, right? Otherwise we decrement it. So shall be able to solve it in over-log-n, and we'll start with a counter of size 32, and what we need to do is go through everyone for int n of nums, right, of nums. So what do is, holy crap, that is not true. Actually, we can't do a prefix sum. We have to do it every single time. My bad. Yeah, we have to do every single time. So So the counter we have to resize every single time, which is okay. Yeah, it's okay. And we need an int res. Okay, res equal to 0. And we say low is 0, high is what is high? High is, let's say, nums dot size plus 1. Okay, we say while low is smaller than high. Low plus high minus low divided by 2, and if mid mod 2 is equal to 1, mid plus plus. Okay, so mid is an even number, okay? And then we'll do the sliding window for everything. So start from the front. So we'll do a counter.resize. Okay. And then what we'll do is we'll go through every single number and we will for int I 0 I smaller than nums dot size I plus plus. Okay, so we will add to it first, right? We'll add to it every single position. So the current number will add to it. So we'll say int current equal to nums I. Okay. Then what we do is we go through all the bits. We can say while current larger than 0. And we also need a j equal to 0, which is okay. It's okay. And we say counter j plus equal to current or 1, right? Current is n1 or all 1, n1, current n1. I'm not sure about the precedence, so let's just do this way, right? So if it's good, then we'll plus. If it's bad, then we will not. And we say current right shift equal to 1, right? We shift to the right, and then we say j also plus plus. So we blah blah blah, we do all that. Okay, once we done for the current, then we check. We say if j, not j, I minus mid, because the first time when we hit is need to be larger than mid, right? Because I is going to be mid minus 1, so minus mid plus 1. If it's larger than mid, right? Because I is going to be mid minus 1. Minus mid minus 1, that's actually larger than 0, right? Because I minus mid, no, I is mid minus 1. So I want this one minus mid minus 1, it becomes 0. That's when we have the perfect length, right? That's when we have the perfect length. So if it's bigger than 0, then we need to minus the previous one, right? So if it's that, then we say int previous. Okay, I actually should put this one int previous. Int previous shall equal to nums I minus mid. Right, this is the previous one we need to remove, and we say and then we reset j equal to 0. And we say while previous is larger than 0, counter j plus plus minus equal to previous and 1, and previous right shift equal to 1. So this is to update the counter. So now everything's updated. Now we say if I minus mid plus 1 larger equal to 0. This means we can check. Okay? Then we check. And we'll say boolean or even. We say it's true. And we say for int counter of counter can say or even and equal to c mod 2 equal to 0. Right, so it's true, true, true. If one of them is false, right? If one of them is false, then we'll get out. I mean, technically we can short circuit it and then just get out immediately, which I think we should do. I'd rather do a check. I think I will do a check for this one. We can say if c mod 2 is equal to 1, then we'll say or even equal to false, and I'll break. Right, and then actually this should be inside because we don't do it. Right, we only do it here, and then once I get outside, we say if or even, which means it's true, then res equal to mid, and then we try to get bigger. So I say low equal to mid. Okay. Else, actually, no. What we need to do is, because I can go through the whole thing as long as one of them is good. Right? One of them is good. Then we'll go. So we should be here. Boolean is good. Is good. Actually, we set it to false, right? And here we say all even, and blah blah blah, and then we say if all even, right? Which means it's good. Then we say is good equal to true. That's it, right? It's if all even is good, and then we're coming here and we say why do you need or even? Yeah, because I need to know when I break out if it's a good or bad. So if it's good as false, then we just keep going. Then we say if is good, then we break it. We don't have to keep going. So one of them is good, we can just get out. Right? If it's not, then we'll continue. Now we get out of this, then we check. We say if is good, then we say mid will equal to, no, low will equal to mid, else high will equal to mid. And usually this will go +1 because it's good, so low become a little bit more aggressive. And then at the end, we'll return low -1 because this is the last one that's good. Then why do you need a result? Okay, let's give this a run. Some condition I didn't. It's alright. We hit some snag. Let's see which part goes wrong. I have some suspicions. Actually, I like to print out the mid as well. Alright, let's see if we can get. It's probably the end condition because this is a. Oh, +2. Yep, that's the one. We got 4, and then you only +1. So I think this should be +2. And then this should be -2. Okay, I'd like to try the other one. Yeah, because it has to be even, so +2. Ugh. Didn't tell you if the other one's correct or not. Why is this no good? So high is 1, low is smaller than 1, and then 0. Yeah, so mid is 0. I is 0. 0 minus 0 plus 1. Doesn't matter, so I just do some stuff. Yeah, so low equal to 2, right? Oh, hold a second. It's not just even. You have the equal number of even and odd numbers. Yeah, it's slightly more. So the last bit has slightly more complicated requirement. So blah blah blah, and then we say it's not everything in the counter, mind you. So it shall be and counter 0, right, times 2 is equal to mid. Otherwise, it doesn't work. Yeah, it's still not working. Oh. What's happening now? It probably got stuck somewhere as well. Let's see, where are you guys stuck? Where did you get stuck? Oh, that's not good. Oh, 4. None of the 4 works. Huh. None of the 4 works. Ah, that is true. That is true. Yeah. Yep, this is not right. Holy crap, this is not right. Wow, I have to think about it. Yeah, that will cost that costs too much. If you go from the largest and you go from the second largest, that's O(n) squared, because each time you go through this, right, and then you have to get that. I mean, we can use prefix sum to make things a little bit easier to compute, but Alright, I have to table this for now. Wow, pick a problem I couldn't solve at the moment. Yeah, I feel binary search doesn't work because a small one doesn't succeed doesn't mean a larger one will not succeed. That's why we got this one wrong. Yeah, gotta think about this. Alright, I'll see you guys.